Alright, so let me take you to 719 West Atkins Street in Dobson and give you a warning. You see this right here? This is a speed limit sign that tells you that the speed limit here is 35. I was taking Hunter over to a music camp at the college, and I apparently did not see this particular sign. Right up above the hill, this way, back here is where it is 55. Right here, 35. Now, I drove along right here at 55 miles per hour until I got, oh no, I didn't mean to go to Hemmons Street here. I did not get here. What did I do? Let's get back. Ah, man. Alright. Is there another sign there? Gosh, that was bad if I went right by two of them. I'm going 55 miles an hour all the way till I get about right here and start to realize, oh, this is probably where I need to slow down. Here I notice it's 25. And about right here, I notice blue lights behind me because I had blown through that 35 mile per hour zone going 55 miles per hour. I don't even know if it was 55. It might have been like 52 or 53. I thought I was not speeding that much. They got me. So, here, I have made a graph of my speed in this particular situation. So, you guys can use your calculators, and actually, we'll do this first one together. I need to know how fast I was traveling in miles per hour at the 0.1 miles from the speed limit sign. So, notice this is a little bit of a weird graph. So, time is down here on the bottom. My distance is here. So, when we're talking about 0.1 miles here, we're looking right here. I want to know how fast I was going there. And so, when I need to find how fast I'm going, what am I looking for that line? I'm looking for the slope of that line. Because if I do that slope, I'm going to use the endpoints here. Because the endpoints will be easier than using different points there. So, I've got the point 0, 0, and then I also have the point 20.3. Okay, so if I do slope for this, I'm going to remind you that it's y2 minus y1 over x2 minus x1. So you'll have 0.3 minus 0 over 20 minus 0, and that is going to give you 0.3 over 20. Now, that 0.3, what am I measuring that in? Miles. And the 20, what is that measured in? Seconds. So, if I take my calculator and, oh, I hope it's still in here. If I take my calculator and do 0.3 divided by 20, I get 0.015. That doesn't tell me much. Why does it not tell me much? It is in miles per second. Speed limits, of course, are posted in miles per hour. So, what am I going to have to do to adjust that? We're going to multiply it by 3,600 because there's 3,600 seconds in an hour, right? 60 seconds in every hour. 60 seconds every minute. 60 minutes in every hour. So 60 times 60 is 3,600. So if we take this and multiply it by 3,600, we'll get 54. So that's 54 miles per hour. So over here I am traveling along at 54 miles per hour. Happy as can be. All right, so I want you guys to now find out how fast I'm going at the 3.5, so that's about right here. And then the last one says at 0.3 miles. So figure those out for me. Okay, so if you're done with that first one, should have got 24 miles per hour there. I just used the endpoints. Right here I'm at 0.3 miles, right here I'm at 0.4 miles, and the time goes from 20 to 35 seconds, so 0.1 miles in 15 seconds. You end up getting 0.006 miles per second, but then you gotta, I should write this down, you gotta 3,600 seconds equals 1 hour. So you got to multiply it by 3,600 there to get the miles per hour. Okay, questions on that part? Okay, now, my last question. How fast am I going at the 0.3 mile mark? I'm glad I'm not getting an answer because it's supposed to be a trick question, right? So what I've got there is this is a straight line. I have a constant rate of change. I was going 54 miles per hour in this part right here. You can see that line steeper than it is over here. Then over here, this is a straight line. It has a slope of 24 miles per hour, right? So according to this particular graph, I went from 54 miles per hour to 24 miles per hour like that, right? Because I've got this sharp turn right here, and there's no in between. Now, so here for this last question, I'm just going to put some question marks. We can't really answer that question because at that point on this left side of that point, I'm going 54 miles per hour. And on that right side, I'm going 24 miles per hour. So, I just like magically drop down to 24. Is that physically possible? It is not. Okay? So, what we have right here is a pre-calculus graph. You guys know how to do the slope of a line, right? It's just a simple rate of change. It's really math 1 stuff right there. So just simple change in y, which in this case is distance, over change in x, which is seconds. So miles over seconds, that gives us our speed, right? So this is what we would be able to do if we're in a pre-calculus situation. When I say pre-calculus, I don't necessarily mean the course pre-calculus. I mean anything before calculus, right? But this is not real life, because you can't go from 54 miles per hour to 24 miles per hour in an instant, right? So if we were going to look at this real life, here's what my graph should look like. So this is the second one. You'll notice everything is still the same, okay? So up until this point, our scales are still the same. The slope of these two pieces of the line are the same, but I have kind of made it a smooth curve, right? Because that's what really happened. I didn't go from 54 right down to 24 immediately. Probably did it pretty quickly because I saw 25 and realized I was going 50-something, and that was not good. So if we look at this, at the 0.1 miles from the speed, 0.1 miles right here, how fast am I going? Again, told you, nothing changed, so we're not actually going to figure this out. It's the same, right? It was 54 miles per hour. Okay? Then, at the point 3.5 miles, right here, it's the same as the old graph. We're not going to take the time to figure it out because it's going to be the same. It's 24 miles per hour. Okay? But this time, whenever I look at this point right here where I'm 0.3 miles, on the first one, I had just two straight lines that intersected right there. This time, I have a curve. Okay? So this is where calculus is going to start to come in. Okay? So what we can do with calculus, and at this point we'll just be estimating. Whenever we get a little more advanced, we will actually be figuring out the exact amount. But what I can think about is right here, I know the slope of this line here. I know the slope of the line here. What I can do is I can put in what we call a tangent line. Okay? So I'm going to draw in this line right here as best I can. And what a tangent line is, it is a line, let me make a different color. It is a line that touches a curve at just one single point. So it just goes along here, just barely touches at that one single point, and then continues on. So let's label that as a tangent line. And so what we can do in this particular situation is we can take this tangent line and we can use it to estimate how fast I was going. Now, in this case, it is going to be an estimate. So if I do that, I need to find a couple points. I'm going to pick these 2 points. I'm going to say I think it's definitely 10 seconds. I'm going to say that's 0.18 miles. And over here, I'm going to say this is 30 and 0.41. I might be a little off on my, realize this is estimating. If it turns out bad, I'll have to adjust my estimates. So if I've got 10.18 and 30.41, now we can find the slope of that graph, right? So if I go down here, we had 10.18 and is it 30? Yeah, 30.41. And so I would do 0.41 minus 0.18 over 30 minus 10, and here like 23.23 over 20, which will give us 0.23 divided by 20 Oh, if you may not have noticed this yet. You probably haven't because we have decimals. I'll show you in a second. But 0.0115, and that is miles per second. We are going to have to multiply that by 3,600, and we get 41.4 miles per hour, which seems like a pretty reasonable estimate right there, right? So I had started to slow down. We know I'm going to be somewhere between 54 and 24 miles per hour. According to our estimate here, at that very moment, I'm at 41.4 miles per hour. I can't remember how fast he actually said I was going. I think he knocked it down whenever he wrote. I think it was still high. I know it was higher than 41. But at this moment, this would be like wherever that cop was sitting with his radar gun. That would, and he, hit the button and scanned my car as I was going by. That at that very single moment, that's how fast I was going. Now, I was slowing down. Well, I don't know if I was. He might have got me before then. But at this point, if he got me right here, I was slowing down. Right? So it was, that speed was changing. Now, if he got me over here, it wouldn't have mattered because I was going a constant 54. It wouldn't have mattered. I would have been the same. Or if he got me right here, I would not be telling you about my ticket right now because I would be going the speed limit. But he got me somewhere before. He got me here or before. I think it was high 40s or 50. He wrote it lower. But anyway, this is that instantaneous speed. It's like that radar gun speed. That is a calculus problem. Now, as we go into calculus, we will learn how to, if we have an equation for this, we will learn how to do this algebraically so we can get like an exact answer instead of just a simple estimate. There's a lot of things that this tangent line stuff is going to show up with that we're going to have to do. So that turns this into a calculus problem. And you can see it's what you really need in the real world, because a lot of times when you're driving, you're not going a constant speed. There are many times when you're accelerating or when you're slowing down, right? So there are many times that you will need to do things like this. All right, I've had 2 tickets in my whole life. I mean, I've been driving for like 20 years now, so it could be worse. Here's my other ticket. I don't have any. That one that he got me on, it was a speed trap. As soon as I came back later that day to pick Hunter up, and he had somebody else pulled over in the same spot. He was just sitting there. He knew people didn't see that sign and we were going to go too fast. It seemed like it was too fast. I guess that still doesn't get me off. But now right here, I have no really good excuse. You guys should be probably familiar with this. This is right here on 268 in front of Elkin Funeral Home and Pleasant Hill Daycare and all of that stuff. Now, had I been going down the hill, it's hard to go 35 down that hill. It's, it's downhill. There's not that much stuff there close to the road. I was going up the hill. I never went this way at this time. This is like 10 years ago. I was picking Hunter up from daycare at Miss Dory's, and I was going up this way. I didn't usually go this way. So, I was going up the hill here at about 50 miles an hour. It is 35. Don't do it. And right about here, I saw the blue lights. Actually, no, I might have already been up to the light, maybe. Is that Wilkes County? Could he have got me there? I wasn't in Wilkes County. Can they go into Wilkes County to get you? I mean, he did. He can probably. I mean, I was in Surrey County down here speeding. I'm sure I was speeding I bet I was speeding right past the park on up. Who even knows? Yeah. 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 I made this 3 or 4. Well, no, this would just be whatever's on Google. Yeah, that is sad, isn't it? That was probably just like a year ago. Whenever Google Maps last updated. Yeah. At least it's not the 447 that it was at one point, but yeah. But 247, that would be nice, wouldn't it? So, So here's my other ticket. So I've made me another graph this time. Okay. So this is my trip to go pick up Hunter. This is the second time I've gotten a ticket. All right. So this I just started with a probably more realistic graph. I was leaving from central office is where I had been. I had been in a meeting at central office and I was going up the hill there. So I did this one in feet, and I've got probably a pretty realistic, graph of my speed. So was I traveling at a constant speed? No, definitely not. You can see here, I'm faster here where it's steeper, slower over here where I'd slow down. During what time interval does it appear I was traveling the fastest? So look at that graph. Try to pick where you think I was traveling the fastest. Okay. Braden says 90 to 100. Anybody else have something different? 60, 70, 70. I think probably anywhere right through here from about 60, 70 up here to 100 somewhere. It looks pretty steep, right? So I'm just going to put, this is 60 to 100 seconds. Then it says during what time interval was Mrs. Hyatt traveling the slowest? What do you guys think? 120 to 130 definitely looks like it. The second closest probably be down here, which makes sense because I was taking off here. I was stopping here, so that's whenever you're going to be the slowest. So 120 to 130 seconds. All right, so now I have made a table, so you should have that table there that you can see. And I'm going to have to flip back and forth, so I've got it printed over here. You guys can still see the table while you're looking at it. So I need you to estimate my average speed. So estimate my average speed for the whole trip. So I'm going to let you guys do that however you would like. And I will warn you, your answer, what am I measuring in here? Seconds and feet. So when you get an answer, it is going to be in feet and seconds. So we will have to change that. And depending on what you remember, probably from chemistry is probably where you did a lot of your unit conversion stuff, I think. I'll go through that real quick. So, yes. Oh, yes. We didn't have that problem earlier because we had decimals. So this will drive you crazy at first on these calculators. The problem is, first of all, what are we typing in? How am I going to find the average speed? All right, 7,530, because that's my distance. That's how far I went for the whole trip, right? I started at 0, went to 7,530. And then I'm going to divide it by the time, and the time was 1:30. And you're going to lose your mind because when you hit enter, it gives you 753 over 13, which is not helpful to you in this particular instance because you want to know an actual number, right? So there are two ways you can get it to give you an actual number. And you're going to have to make this habit, and it's going to drive you crazy at first until you make it a habit. So the first way is to hit the green button. So my green button looks a little different than yours there, but it's that green button right below the blue button, and then hit enter. So if you hit the green button before you hit enter, it'll give you a decimal approximation. The other thing that you can do is if the numbers you are multiplying, dividing, adding, or subtracting have decimals, it's going to give you a decimal answer. So you could just do 130 and put a decimal point behind it, and it will give you a decimal for that. But if you just type in two numbers that you're dividing, it's just going to reduce the fraction. There are going to be times where that actually ends up being really great for you and helps. But until you get used to having to hit the green button before you hit enter, it's going to drive you crazy at first. So we did 7,530 divided by 130, and it gave us, let's see, let me make this work. It gave us 57.9234. But this was feet, and this was seconds, so that means our answer is in feet per second. Okay, so we're not going to do a ton of this, so I'm not going to go through in depth. But for these, we got to change that to miles per hour to really answer this question, because 57 feet per second, unless you really do a lot with feet per second, you don't know how fast that is in miles per hour without converting it. So feet per second, the way that I was taught to do this is if you have feet on top and you need to get rid of feet, you're going to put feet on bottom. And what unit do we want to change feet to? Miles. Okay, so we need feet is on top, so we're going to put it on bottom so it'll cancel. How many feet are in a mile? 5,280. So we're going to put 5,280 feet on the bottom. We're going to put 1 mile on the top. And then, so what that does is it cancels out feet here with feet and has changed this to miles. We also have seconds on the bottom. Do we want our time to be seconds? We want that to be hours, right? So seconds is on the bottom. If we want it to cancel, we have to put seconds on the top. What do we want to change seconds to? Hours. So it's going to go on the bottom. And we did this a little bit ago. How many seconds are in an hour? 3,600. 60 times 60. And so what that does is we've got seconds on top and seconds on bottom, so those cancel. So when we multiply this all together, we're going to get our answers. Our units on the top are miles, and our units on the bottom are hours. You guys do this in chemistry? Maybe? Yeah. It is really something you're going to use a lot in your science classes in college. Like if you're going to take a lot of science classes, you will use it a lot. I'm not going to say we're going to use it a ton in here, but it's good to know. I'm not going to spend tons of time on it. So we're going to take that 57.923. We're going to multiply it by 1 over 5,200. Oh, wait. Times 1 over 5,280 times 3,600 over 1. You don't have to put over 1 if you want. You really could just multiply it by 3,600 over 5,280, because if you multiply those two fractions together, that's what you get. And we get 39.493. Now, if the cop had just looked at my average speed, I would have been speeding, but only by 4 miles per hour, and they probably would not have pulled me over for 4 miles per hour, right? But cops do not look at your average speed. Cops have a radar gun, and they shoot your car with the radar gun, and whatever it says is how fast you're going, all right? They don't care if you were going slower before, and now you've sped up. It's however fast you're going at the particular time. If you get caught going 120 miles an hour on the bypass, the cop is not going to care that you were only going 20 for the first part and then 30 for the last part. So really your average speed was just 55 miles per hour. They're not going to care. I promise that they will not care about that. So don't do it. But my average speed, I would have probably been okay. Probably would not have gotten a ticket. So what we're going to do is we're going to estimate my speed at 20 seconds and at 65 seconds. Okay? So at 20 seconds, if we look at that table, 20 seconds is right here. Okay? What we do not want to do is we do not want to say I had gone 930 feet in 20 seconds. Because that would give me my average speed for the first 20 seconds of the trip. I was probably going slower here because I was just taking off, right? So I was going slowest there from 0 to 10, and there at the end where I was slowing down. So if we want to find an estimate here, what we want to do is we want to take the closest points we can get and find that average, or find that speed, right? So we could use the time from 10 to 20. We could use the time from 20 to 30. We could use the time from 10 to 30. Really, any of these would be acceptable estimates. Those points right there really close. Let's see. I think what I did is I went, what did I do? I think I used 20 to 30. 20 to 30 is going to give us probably a little bit of a fast estimate because I'm probably going slower here and faster here. But I did 20 to 30 there. So if I find the 20 to 30, oh, wrong thing here, then at 30 I had gone 1440. And then at 20, it was 930. And then here, it was just 30 minus 20. And that is going to give me 510 over 10, which is going to give me 51. But remember, this is feet per second. And so to change it to from feet per second to miles per hour, I can do that 3,600. I'm not going to do it out the long way like I did before, 5,280. That will change our feet per second to miles per hour. So if I take 51 and multiply it by 3,600, divided by 5,280. Green button. Hit the green button before you hit enter. I've got 34.7727. Okay, I'm good right here. Nobody's going to pull me over. I'm under the speed limit, right? Nobody's going to pull me over. But let's estimate my speed at 65 seconds. Now, 65, it's pretty clear what we need to use because 65 would fall right here between 60 and 70. So we want to find the slope between 60 and 70. We do not want to do 4,130 divided by 70. That would give me 59, which if I multiply it by 3,600 divided by 5,280, that would give me 40 miles per hour. I would have probably not been pulled over for 40 miles per hour. If I do that, that gives me the average speed for my whole trip. Cops don't care about average speed. They want to know how fast you're going right now, right? So my best estimate is to use 60 and 70 as my endpoints. So at 70, it's 4,130 and 3,380. And then that'd be 70 minus 60. So here, I got 75. Remember, we're feet per second. I was not going 75 miles an hour up that hill. That would have been really bad. And if I multiply this by 3,600 over 5,280, green button, enter, I get 51.136. Sadly, this was how fast I was going up that hill, and I got a ticket for it. So, watch out over there. I would call it a little bit of a speed trap if I've been going down the hill, but I was going up the hill. There's no good excuse for me. Here, I was just driving too fast. What I'm getting at here that I want you to see is that average speed over a time is that straight line distance, right? That instantaneous speed, we're wanting to zero in on the actual point. Now here we couldn't get to the actual exactly at that point because we didn't have data points close enough, but we could zero into what's the closest piece of information we have, right? So I might not have been going exactly 51, but I was close to 51 because it was close to in between those 2 points, right? So are you guys kind of picking up on the difference between that instantaneous speed right at that moment versus looking at average speed, right? Average rate of change is going to be the change in your y variable divided by your change in your x variable over whatever period of time that you are looking at. That change in your x variable is typically, usually if time is one of your variables, it's usually on the x-axis, but not always. Instantaneous rate of change is going to be that slope of the tangent line. We still find slope using change in y over change in x, but it's not of a period of time. It's at the tangent line there. So, we are not going to get through all of this today, as I thought we might not. I do want us to watch this video because it's really cool, and it is about 10 minutes. I need to give you, though, let me give you the homework assignment before we start this video. So, there is something on Canvas that is a worksheet. We're going to do that tomorrow because we'll finish up these notes tomorrow. So, this is going to be your homework assignment, and for it, you will need your book, pages 58, 59, and 60. So if you want to take your book home, then you don't need to worry about it. But if you don't want to take your book home, you can get your phone and take a picture of those pages, 58, 59, and 60 are the pages that you'll need for this assignment. So the book has a really good, in my opinion, short introduction to calculus. There's just like a page to read, and there's a couple pages of some examples that they give you that kind of looks at the question of what in the world is calculus, right? What is this that you guys have gotten yourself into? What are we even going to be studying, right? So this is going to be your homework tonight. The assignment on Canvas that says it's classwork, that worksheet, don't worry about that. I'm going to move that to tomorrow. So you won't be doing that. So for tonight, I think everybody finished their student information survey. If you didn't finish your parent information survey, please do that for me, and then you'll have this assignment right here. 58, 59, and 60. So, once you have taken pictures of that, please put your phones back away to watch this video. My understanding is going to be an emphasis that kids don't just have their phones out this year. So, Miss Burton and I guess Mr. Foster. I want to call him Coach Foster. Mr. Foster sounds weird. Maybe he's still Coach Foster. I don't know. They're just going to run over. They're going to run over like any changes that are happening this year, and so. Yeah, we'll go. It'll be in the auditorium. I think it's not. You'll have like 25 minutes to begin the second period, and then I think it's 10:25. Maybe. Do you have a second period, or are you one of the very few that does not? Do you have another class you have to go to? Yeah. Yours is online. How about yours? Oh, online. I think you're expected to go there. I think to the meeting. So maybe go up to Mr. Sugart's room for a little bit, and then go down there to the meeting, because I think they want everybody to be there. So you won't have to do that, of course, except for today. All right, so we're going to watch this video. You can put all your stuff away if you want. This will take till the end. Calculus is so cool. Yes, calculators can go home. They're yours. You've got to keep up with them. I expect I'll just put it in your book bag, keep it there. Let's see, I got to get my, oh no, sound's not working. All right, calculus is so cool. There's so many cool things that you can do with calculus. Now, we are Calc 1. This is freshman in college sort of level stuff. We are not going to be designing roller coasters by the end of this class. I myself don't know how to design a roller coaster, but we're going to learn some basics of it. So let me see if I can get the sound to work. Okay, I got it on. I think I needed this. Okay, let's see. Oh, I've got it also on 0. Of course, that's not working.
And extreme forces in relation to everyday life for most people cause the body to feel it.
It does so much louder against the projector, but I think there's something I got to put. There's maybe this. Oh, there we go. Alright, we'll start. I hope we get to go to Carowinds this year. Even though I'm getting way too old to ride roller coasters. I get dizzy so bad. Going to Carowinds at the beginning of the season on like a Wednesday or Tuesday. We used to go like a Tuesday or Wednesday. You could, like, kids would ride like the Fury like 5 times in a row without getting off. Okay, why is it still so? Well, let's go back. Oh, that's why. Let's cut that up to 100. Okay.
Right. Extreme forces in relation to everyday life for most people cause the body to feel in danger, which triggers the release of chemicals in the body, most notably adrenaline. The thrill comes from surviving the roller coaster. Of course, roller coasters are perfectly safe, and it is this controlled fear that provides the rush. G-force is nothing more than another unit of acceleration. It is designed as a more intuitive means of communicating the strength of differing accelerations. The normal acceleration due to gravity on the Earth's surface is 9.8 meters per second squared, which is equal to 1 g. If you were to stand on the moon, a smaller body with less mass, where the acceleration due to gravity is 1/6 of that on Earth, you'd experience 1/6 of a g, or roughly 0.16 g. Whereas if you were to stand on Jupiter, a far larger planet than Earth with greater mass, the acceleration due to gravity is around 26 meters per second squared, which also equates to 2.65 g.
The thing that's different about a birthday vacation home, you always know the whole place to yourself. Just you and your people.
The same is true for accelerations we experience undertaking different activities in our lives. If you accelerate in any direction, it can be said that you're experiencing some additional g-force, as compared to just simply standing still. It is worth noting that acceleration must be thought of as a vector. That is to say, it has direction, just like velocity. A train taking a circular corner at a constant speed has changing velocity vectors, and therefore has acceleration forces. In this example, the acceleration forces in both directions are resolved into one acceleration force towards the center of the corner. For you to remain in the seat and not be thrown from the train, the seat must exert a force on your body. It is this acceleration that is referred to as the g-force. For roller coasters, it is accelerations in all different directions that create the g-forces we know and love. Three commonly used types of g-forces on roller coasters are vertical g's, lateral g's, and acceleration g's. Vertical g's are the forces pushing you down into the seat, or up out of the seat in the case of airtime. If one imagines sitting in a roller coaster seat, vertical g's are the forces you experience at the bottom of a drop as the train pulls out and you feel heavy. In the same turn, airtime is the experience at the top of a hill that causes riders to feel weightless due to negative vertical g's. Lateral g's are the forces you experience sideways. A great example of this type of g-force is that found on Wild Mouse coasters, as the tight, unbanked corners provide lots of lateral g's, making the train feel as if it will tilt over. Acceleration g's are the forces pushing you backwards into the seat, most often found during launches. Brake runs also cause acceleration g's. However, as they are negative, the train is slowing down, you are pushed forward out of your seat and into your restraints. In addition to these three main types of forces, there are also g-forces accelerated with the rotational aspects of track shaping. These forces, however, are often much harder to directly feel. The most evident and most commonly felt type of g-force like this is the track rolling. The famous whip and B&M flat spins, or zero-g rolls, are a result of this kind of rolling acceleration. The amount of g-force the human body can withstand is dependent on many factors. These can include your fitness, training, hydration, and nourishment. Ever notice how you might feel lightheaded or black out on a roller coaster when hungry or thirsty on a hot day? The risks from experiencing high g-forces vary, but the key issues are a lack of, or excessive, blood flow to the head, or disruption to internal organs. A frequent key factor is the duration of time that the g-force is experienced for. During a car accident, the human body may experience many tens of g-force. However, this is only for an extremely short period of time. Typically, however, we only refer to g-force that occurs over a period of time that can be measured or sensed. The average person can withstand g-forces of up to 6 or 7 positive g-force and negative 3 to 4 g-force for short periods of time without suffering too much long-term discomfort. That said, roller coasters are generally designed between the negative 2 to positive 4 g-force region to ensure rider comfort. The additional g-force you experience at the bottom of a drop that makes you feel heavy is a result of the train being accelerated away from the ground. The seats are exerting a force on the riders to change their direction. G-forces of less than 1 are a little more complex. The equations of motion give us some interesting results. An object launched into the air at an angle will follow a path of a parabolic motion. For getting air resistance, as is often the case in these kinds of thought experiments, the path the object will take is dictated by the acceleration due to gravity. During its journey along this path, the object is accelerating at the rate of acceleration due to gravity. Remember, that's 9.8 meters per second squared here on Earth. In this instance, the object has nothing pushing back on it, meaning it experiences 0g. Roller coaster designers use this physics to their advantage. If the engineers calculated the path the train would take if the track simply ended, and then build the track along this path, they would have created a hill with perfect floater airtime. If the train was traveling faster than this track shape was designed for, the train will be forced to follow a tighter curve. At this point, the riders in the train, if not properly restrained, would leave their seats and continue on the previous path. As your bum leaves the seat, the restraints hold you back in place and leave your internal organs to experience the feeling of being accelerated upwards. By varying the sharpness of the curve, manufacturers can control the amount of negative G-force well. This form of ejector airtime is often popular with enthusiasts. Floater airtime is best experienced in B&M hypercoasters, which are famous for creating
We didn't quite get
near-perfect
finished there,
zero
but
G-force hills.
just make sure you have that